All right. So, notes week 5, part 2, we're learning about Newton's laws. So, Newton's third law says for every force there's an equal and opposite force. And the example that I like to talk about is this. So this is not shown to scale, but we have the Earth and we have a happy physics teacher jumping. And so as you're jumping, you definitely feel the Earth pulling downward on you. And what's hard to believe is that you are actually pulling up on Earth with the same force. So that's the way things work. Earth is very massive. We'll draw a really big M. And I, relative to the Earth, am very not massive. So the acceleration that I experience is very great relative to the acceleration that Earth experiences. So we can say this. We know F equals ma, and the force that each of us, meaning me and the Earth, experiences is the same, or the magnitude is at least. I get pulled downward by Earth, and I pull Earth upwards. So the same force means that for me, mass times acceleration is the same as mass times acceleration for Earth. ma equals ma, and maybe I should use a big M for Earth. Yeah, here, I'll draw it like this. Sorry, erase that or cross it out or whatever. So me, let's see, I have a little tiny mass and so a big acceleration, and Earth has big mass and so small acceleration. All right, so instead of actually writing in big numbers, this is kind of how we can represent that. But for every force, forces do not exist in isolation. They come in pairs, and so we call those action-reaction pairs. And if we look at, let's call this a box on a desk, we have an action-reaction pair going on here. And one is that the box is pushing down on the table. So this is box pushing, I'll say everything, I'll write everything, just to be thorough. Box push down on table. And the opposite of that is the table pushes up on box. And so that's the way things work. When you push on the door pushes back on you, and you can actually feel that. Okay, and they're going to have equal magnitude, opposite direction. That's some good vocab right there. Equal magnitude, magnitude meaning amount. Equal magnitude, opposite direction. Okay, hey, direction. So, action-reaction pairs, that's different from a free body diagram. And so we've talked about free body diagrams, or maybe we haven't, but the idea behind a free body diagram is we're pretending whatever object we're interested in is free of other stuff around it, okay? So, free body diagram for the box, we're just considering forces acting on object. And if we think about the box, there are two forces acting on the box. One is gravity pulls downward, and so we can call this the force due to gravity, aka weight. And the force that opposes that, so the box is just sitting there on the table, it's not accelerating, the net force on it is zero, it is in equilibrium. It's a lot of terms right there. But basically, the two forces acting on it cancel out. And so gravity, or its weight, pull downward, and table push up. Table pushes up. Caveman speak. Okay, so a free body diagram would actually be like this. We wouldn't draw the table. We would just draw the box. And sometimes people are particular about the forces emanating from the center of the object. That's not a big deal, but it's basically like this. So we could say gravity and we could say table. Notice how I've drawn those arrows so that they have the same length within artistic license, indicating that they have the same amount of force, the same magnitude, or the same number of newtons, but are in opposite directions. Okay, so that's a free body diagram. The excellent question is, if everyone in the world were to come to Mammoth, I know it'd be pretty crowded, feel like one of those, imagine the lines at Vaughn's, ha ha ha, and jump up to a height of 1 meter, for the sake of example, what acceleration would the Earth experience? You know, would we cause an earthquake? And if we did, would it be a magnitude of 1 on the Richter scale, or a magnitude of 9, and would buildings crumple and all that kind of stuff? So there are some things we'd have to assume, but we could definitely calculate that. And I think that's going to be an extra credit project for you. So difference between net force and normal force, because both of these involve ends, and I hear students kind of not really use these terms correctly. So let's first draw a free body diagram of an airplane, and this will help. So the airplane looks like this, obviously. It's my Shamu airplane. And when the airplane's flying through the air at a constant speed, meaning the force in the forwards direction and the force in the backwards direction cancel one another out. It has no net force in the forward direction, and it is not accelerating, okay? And constant altitude, meaning the force in the upwards direction and force in the downwards direction are also balanced. So our cute airplane looks like this, where we have a force in the forward direction, and that's due to the engines. I didn't draw my airplane with the engines, but you know. And so in terms of aeronautics, we call that thrust. So that's the force in the forward direction. And the plane in the real world is obviously going to experience air resistance. Planes take a huge amount of fuel, for example, to fly to New York, as compared to putting those people on a bus. And then gravity obviously pulls downward. And if you call this gravity or if you call it weight, those are both perfectly acceptable. And then the airplane has these funny things sticking off of it called wings, which help provide what we call lift. So those are these are some aeronautics terms that aren't on the list of things that you have to know, but here's a free body diagram of an airplane, and so we can say some things. We can say that the net force on it is 0. Okay, 0 newtons. That does not mean that it is not moving. The plane is obviously moving. What that means is that there is no acceleration. Okay, no acceleration, meaning the constant speed. Okay, we can also say that the plane is in equilibrium. And equilibrium means, sorry to be writing all over my writing, equilibrium means the forces are balanced. Forces are balanced. Okay, so there's our free body diagram. We didn't draw any planes or pelicans or whatever. But let's talk about net force versus normal force. And so by net force, I know some people think of like Spider-Man or whatever with these nets. Net force, so that is the result of all the forces. That's as a result of all. Sometimes people describe it as the sum of all the forces, and so that's fine as well. But the idea is that when we talk about the net force, and so this is how you'll see it written, F sub net, the net force is what we are referring to in F equals ma. So that right there is the net force, meaning the result of all the forces acting on the object that thus cause it to accelerate. So in the case of the plane, the net force is 0, and its acceleration is 0. In terms of a box sitting on the table, we definitely have experience with this. Table pushing up, gravity push pulling down, and the net force is 0. The forces are balanced. That says 0 newtons, not on. Okay, result of all the forces. Now, normal force, F sub capital N, normal is a mathematical term that, and we brought this up before, but I'm going to say it again because at this point, if you don't know it, it's important. This means perpendicular. All right, so normal to a surface, all these little lines I'm drawing, these are normal to the surface. If I get a buzz cut, my little hairs stick up, normal to the surface. And so it's indicated like this, and in the case of the box, the normal force would be the force on box perpendicular to table. And in the case of, well, so in the case of the box on the table, it's the force of the table acting on the box. It's not a free body diagram. We're not calculating the acceleration due to gravity. We're just talking about the normal force. So that term comes up a lot, and I thought it important to mention. Let's take a look at page 2 in the second video, because we're going to run out of time.